So let's look at the best linear estimator. You are given a data set. Data is x1 through xn. Data is of course known, and y is our unknown. Y could be part of this time series. Why I call it time series because xi could be from a stochastic process sampled at some time ti's. Ti's doesn't have to be uniform, it could be uniform. For example, ti could be some I multiplied by t, where t is the sampling interval, or you could unequal samples also. In any case, y is unknown, and we want y to be a linear function of the data set. So I equal to 1 through n, ai, xi. Ai's are the unknowns. So the question is, how do you select the best ai's? So you could look, question is, we want the best estimator. So the question is, what do we mean by best? So as we discussed earlier, the best could be in terms of minimizing the mean squared error. So this could be minimization of mean squared error. So this is a criteria used universally, MMSE, minimization of the mean squared error. So of course, to minimize the mean squared error, first we need to figure out the error. Error is, as you said, the difference between the exact value and the estimator, y minus sigma ai xi. So I put the subscript L to remind us that we are dealing with the linear case. So if you minimize this quantity is the same with respect to, of course, the minimization is with respect to the unknowns. So this being a quadratic, it should turn out to be a quadratic function. And so when you take the derivative with respect to aj, you can see from here it is epsilon multiplied by, because this is epsilon squared. So that the derivative is epsilon multiplied by the derivative of the epsilon with respect to aj. But that derivative is from here, it's only xj. So you equate that to 0. So the bottom line is that derivative turns out to be epsilon star xj equal to 0. Or if you take the complex conjugate again, you can write it like this. Epsilon xj star equal to 0 for all j equal to 1 through n. So if you look here, this is two random variables. If they have this property, we call it the random variables to be orthogonal. So this is known as the principle of orthogonality. So what's the bottom line? The best linear estimator leads to principle of orthogonality. So best linear estimator principle of orthogonality. Orthogonality between what? So you have the error, which is y minus sigma ai xi, and you have the data set x1, x2, etc. xn. So this is the error. What the orthogonality says is expected value of epsilon xj star equal to 0, j equal to 1, 2, etc. So if you want to write, it says error is orthogonal to the data set. So you choose the constant such that the error should be orthogonal to the data set. So your choice is where? Your choice is in selecting these AIs. So this best linear estimator, these AIs will be selected such that this error will turn out to be orthogonal to the data. So, let's use that condition and see whether we can solve for A's, okay? So always remember this. So again, let me make sure you understand. you have error. So the only freedom here is the AIs, how to select the AIs. You have n AIs, and fortunately we have n equations, so we should be able to do well. So these AIs should be selected so that this error is orthogonal to each and every data set, not few of them, all the data sets. So you do get n conditions. So let's see how that comes up. So I can expand this and get the set of conditions, and so let's do that. We have expected value of epsilon xj star, and let me substitute for epsilon. So this is y minus sigma ai xi I equal to 1 through n multiplied by xj star is 0. So that I have, so I'm going to write this as ai expected value of xi xj star equal to, right? I just took the y term to the other side, or I took the x term to the other side, etc. What is this? If you think of this as expected x of ti x tj star, what is this quantity? Autocorrelation. See again, autocorrelation is coming into estimation. So I equal to 1 through n. So this is ai or xx, let's say ti comma tj, and what is on the right side? This is what? Cross correlation. So this is ryx. Let's say for the time being I'll denote it like this. I mean this itself could be x of t naught or something, but let me simply denote it as r of y x j, right? Or if you don't want to use the r symbol, I'll use gamma, just a notation y x but corresponding to time tj, or gamma j. If you want, you can also write this as, you know what it is, it's gamma j, it's just this quantity. I equal to 1 through n. So if you want, we can put this up into, this is a set of linear equations, you see. Right? So you have unknowns a1, a2, x. So what will be that? So let me, rather than write like this, let me put a notation here. This I'm going to call it rij also. So this quantity I'm going to denote it as either way. So what will be the number here? Anybody? How will you fill this matrix? R11. Right. So hold on. J is moving or J is not moving? So you just, so we can, so this will be R21, right? I is going to 2, right? So if you want the other matrix notation, let me call this RJ, just a notation. Then this would be R11, R12, right?
Yes.
Because I is here. I is, so do it for, yeah, so J, this is, do it first J equal to, so this is for J equal to 1, right? So this is R13, right, etc. R1n, right? Then R21. But you remember R21 is the, this is the same as, it doesn't matter, Rij star, isn't it? So this will be R21 or R12 star, R22, etc. R2n, etc. Rn1, Rn2, etc. Rnn. So this is a autocorrelation matrix. which is non-negative definite. But you see, if you knew a little bit, this is of the form RA equal to something, AX equal to Y. So we can solve for these unknowns. So let me call this matrix to be capital R. And let me call this to be gamma vector. Okay. Remember, this whole thing is R. And let me call this to be A vector. So I have RA equal to gamma. What is the solution for A? Anybody? R inverse gamma. So if you want a vector notation, we are here also. Here you could write this as, see, this one you could write it as x1, x2, etc., xn. Then you have a1, a2, etc. Okay, right? So this A is what looking for. So this, if you call this to be x, then this is x A, right? I'm going to call it x transpose because x is a column vector. So we are looking for A, or you could leave it. So I solve for A. The A vector is R inverse gamma. Now there is one more item here we have in the, so we also look at the minimum mean squared error. This is the minimum value of expected value of epsilon squared. When epsilon is minimized, what is the property between error and data? Anybody? When you are at the right, when you have minimized the epsilon, what is the property between error and data? Orthogonality. So we should make use of that orthogonality here. Look at here. So this I can write this as expected value of epsilon multiplied by epsilon star, right? Yes. But now look at the argument now. So I want to minimize A, but epsilon itself is so this epsilon multiplied by epsilon star is what? Y minus summation AI xi star. So this is y star, and this is y star. Where is it? This is star here. This is star here, right? So this has two terms: minimization of A expected value of epsilon y star minus summation I equal to 1 through n AI star expected value of epsilon xi star. So what happens to the second term? Anybody? Why? Look at here. When you have chosen the correct AIs, if you have minimized, what's the relation between error and data? Orthogonal, right? So these AIs have to be at the right stage. AIs have to be such that the expected value of this is 0. So this term simply turns out to be only the first term. So this is expected value of, let me substitute for epsilon. Epsilon is x star. Look at here. So this is so your epsilon is y minus y hat. So this is y minus x star A from here. So what is x? X I'm assuming it to be like this: x1, x2, etc., xn. This is the data vector. Its transpose is this multiplied by. So all my vectors are column vectors. So for epsilon, I'm going to substitute this there. I didn't substitute it properly. So let's go here. Right? So look at this. This is, so maybe I'll pick it up here. So sigma squared minimum is just the first term, right? So it's simply expected value of epsilon y star. So epsilon from there, epsilon is expected value of y minus x star a multiplied by y star. Remember, y is a scalar. So this is expected value of y squared minus x. I can bring this y here because this y is a scalar. So this is x star y a. So finally, x star y is here. So let me. So look at here. What is this gamma vector? Look at here. Gamma is here. Gamma 1 is. Where is gamma? Gamma 1 is here. See, gamma 1 is y xj star. So this first entry is expected value of, look at here, y x1 star. The next, so this is going to be like this. Next entry is y x2 star, etc. Expected value of y xn star. So that's gamma. What will be gamma star? Yeah. Or in fact, this is what you need there. If you look there. Hold on. Let's see whether maybe I made a mistake here. This is star is here, right? Epsilon is y, so x star x y star a, right? Right. Huh? X transpose, right. So that's going to be, and from here, if you want, this is y x star, right? So if you take the transpose of that, you'll get that one. You see that, right? X, y. So this, if you want, I can write this as symbolically expected value of y x star, right? Because x1, x is what? x1, x2, etc. tagged along. So the star of this, so gamma star will be from, you should be able to see that gamma star is, for example, expected value of x y star. And that's what we need there. So this is sigma y squared minus this is gamma star multiplied by a. But a is already here. So if you substitute this, this is sigma y squared minus gamma star r inverse gamma. But this will be a scalar, and because it is variance, it cannot be negative. So you also get that this quantity is positive. That means this term, whatever is this, has to be less than this. So that's the moral of the story with respect to linear estimation. The best linear estimator, the unknown coefficients obey the orthogonality rule. And so if you ask me ultimately what is the minimum most error, that's the minimum most error there. Remember, we did the nonlinear case earlier. The best estimator, linear or nonlinear, is conditional mean of y given x. And what was the corresponding error? When we did everything, we got the error to be expected value of variance of y given x. Which quantity will be, which is a better estimator, this or this? The first one had no conditions. In the second one, we were limiting because it's linear estimators. So which estimator is in general better? The nonlinear estimator is a superior estimator. That means its variance is the error you get, error has to be what? Compared to this, which one will be smaller? So this is a superior estimator. So this error will be less than this. So you could blindly say at this point, this error is larger than, this error is smaller than this. The relation between these two quantities are like this, right? What is this gamma? It's there, the correlation between x and y. What is this R? Autocorrelation entries. What happened to A? A is sitting here, right? And same, of course, this is more complicated because of the joint density functions, etc.